Hello, chemistry class, and welcome to Module 10. I'm kind of starting in the middle of Module 10 because we've talked about some of it in class already. But anyway, we're going to review some stuff about acids and bases. Acids, remember, are going to be things that donate a proton or an H+ donor. Bases are kind of the opposite. Bases are going to be a proton acceptor. Things that you can add an H+ onto are going to be known as bases. We've also talked a little bit about what happens when we add an acid plus a base. And you'll remember from class that anytime we add an acid and a base in a solution together, we are always going to get a salt and water. This is also known as a neutralization reaction because the salt is not going to make any kind of pH change in the solution. And water, of course, it already has a pH of 7. So we're going to take things that have a low pH and things that have a high pH and make something that is much closer to 7, or a neutral product is going to be formed. Okay. So we've talked a lot about lots of different kinds of acids and bases, but let's do a couple of examples. For example, right now I am looking at an example on page 332 in your textbook where we have HNO3 plus AlOH3. And we want to know what we get. So this is going to be our acid, and this is going to be our base. And what we're going to do is we're actually going to be separating this into its ions, and we will be producing with this hydrogen and these hydroxides, we're going to produce a water, and we're going to be left with an aluminum nitrate. Now we have to make sure that that everything balances, so let's make sure that we have the same number of atoms on every side. But before we do that, we've also got to make sure that our molecules are balanced. In this case, hydroxide has a -1. That means aluminum is going to be a +3. Aluminum has to be a +3 on this side as well. And the nitrate is going to be a -1 because the H is a +1. So this is going to be a -1, which means we're going to need 3 of those nitrate polyatomic ions in order to get that molecule to balance. Okay. Now all of a sudden we have 1 aluminum here and 1 aluminum there. We have 3 nitrogens and 10 oxygens. Here we have 1 nitrogen and 6 oxygens. So since I have 10 of those oxygens, and well, first of all, I'm going to need another two more nitrogens. Since I have 1 here, that should be fixed by putting a 3 here. Now I have 9 oxygens, and 3 is going to be how many oxygens total? 12. Since I have 9 here, 10, putting a 3 here should fix that as well, right? So again, 9, 10, 11, 12 oxygens. 3 and 9 is 12 oxygens here. 3 nitrogens, 1 aluminum, 1 aluminum. Hydrogens are what we haven't counted yet, so I've got 3 hydrogens. This is 3 more, so that's 6 hydrogens. 6 hydrogens here. It's now balanced. Okay, and that is going to be how we balance an acid-base reaction. You have several other examples that you can do on your own. But sometimes we're going to be dealing with a base that doesn't have a hydroxide on it. Remember, our bases are we're going to be thinking those as proton acceptors. And when we use a proton acceptor that's OH, we're going to be making our H2O. Sometimes we'll have a reaction going on where we do not have a hydroxide ion on our whatever is acting as a base. For example, I'm going to do H2Cr2O7 plus water. Okay. Again, we have to think about what's going to be our acid and what's going to be our base. Is this going to be our acid, or is this going to be our acid? Well, this is actually going to be our acid this time, and we're going to end up getting an HCr2O7 if we remove one of those hydrogens. But we can actually remove both of those hydrogens because this is a diprotic acid. You can look that up in your textbook. So this is going to be a Cr2O7 2 minus plus H3O plus. Water will be our base because it accepts that proton. And we need to balance it again. I've got 4 hydrogens on this side. I have 3 on this side. What else is going on? If I see, I've got 4 and I've got 3, so in order to make 4 and 3 balance out, I'm going to have to put a 2 here and a 3 here. Now I've got 6, and I'm sorry, I've got 6 here. Sorry. I'm going to have to put a 2 there and a 2, so that makes 4, 5, 6, and I've got 2 oxygens and 2 oxygens, and I think that balances now. So this is an example of what happens with a diprotic acid. We can also do something when our base is not water, which is the one I meant to do a minute ago. And so which of these two things can be our acid? This is going to be our acid this time. We should know that ammonia is a strong base. NH3 is ammonia. So this is our proton acceptor, and we're actually going to put 1 proton on there and make that a positive charge. And we're going to take all 3 of those protons off and make that a 3 minus charge. And now we've got to make sure we balance everything. So we have 6 hydrogens. Here we only have 4. We have 1 phosphorus. We have 4 oxygens. We have 1 nitrogen on either side. So how are we going to balance this? Well, since I have 3 here, 3 and 6, I am going to have to do something so that I increase this. Now 3 and 6, the lowest common multiple between 3 and 6 is 12. So I'm going to guess by putting a 3 right here that will give me 12 hydrogens and 3 nitrogens. And now I'm putting a 3 here. That gives me 3 nitrogens, 9, 10, 11, 12. Now my hydrogens balance. My phosphorus and oxygen are still balancing. So that's how we're going to balance this reaction. Again, this was our base because all of these protons flew off and they flew onto the NH3, which makes the NH3 the base. Acid, base. And that's something you should know. Anytime you see NH3, it's going to be pulling off that hydrogen. That's something, just a rule of thumb that you'll always know. This is always going to be a base, and the other thing there will be an acid. Okay, so now that we reviewed a little bit of what we've already been talking about, we've seen a lot of, we're going to move on and discuss molarity. Molarity is a new definition. It's just something to know. It's not something that somebody had to discover. It's just a way that we talk about concentration. Molarity, by definition, is always going to be moles per liter. So if you know the number of moles of something and you know that you have a total volume of a particular number of liters, you can always figure out the moles per liter. You can always figure out the molarity. And again, this is a definition. This isn't something that is discoverable in any other sort of way. It's just a definition. So if we have a question like page 335, where we're talking about example 10.4, what is the concentration in units of molarity of NaOH if there are 2.6 moles of NaOH in a solution that has a total volume of 534 milliliters? Well, if you know the number of moles and the number of liters, you're good. All you have to do is divide. Do we know the number of moles? Yes, we do. The problem tells us that we have 2.6 moles of sodium hydroxide. The number of liters, do we know liters? Well, we don't know liters, but we do know milliliters. And we can change that pretty easily because we know that 534 milliliters is going to be 0.534 liters. And you can always do the dimensional analysis to figure that out for yourself. 534 milliliters. There are always 1,000 milliliters in 1 liter. So if you do that math, the milliliters cross off, and there was not a decimal there, not supposed to be. So 534 divided by 1,000 is 0.534 liters, just in case you couldn't do that one in your head. So anyway, now that we know the number of moles and the number of liters, to find the molarity, capital M, always a capital M, never ever a lowercase, we are going to do 2.6 moles divided by 0.534 liters. And when we do that, you can put those numbers into your calculator. You should come up with 4.9 moles per liter NaOH, or 4.9 molar NaOH. So that's how you're going to be calculating the molarity of a solution. Okay. Any questions on that? You can always pause the video and back up and look at it again. Okay. We are going to move on and talk about another example of that. For example, maybe we have 124.3 grams of nitric acid. And we are going to put it in enough water so that it adds up to 250.0 milliliters of solution. Now remember, I can't start with 250 milliliters. I have to put this mass of our acid into the beaker, whatever I'm diluting, whatever I'm measuring in, and then I'm going to add enough water to get to 250 milliliters. That's an important detail when we work things out in the lab. So anyway, if I start with 250 milliliters and I put this in, then all of a sudden my whole solution is going to be more than 250 milliliters, and our calculations will be off because we have the capability of getting very, very precise measurements when everybody does things the same way. So we are going to start with our mass of acid, and then we're going to dilute it up to a total volume of 250 milliliters. So remember, if we want to know molarity, molarity is moles per liter. So I have mass in milliliters. Can I just stick them in here and find molarity? Well, not really. First, I have to go ahead and find my the number of moles of nitric acid that I have, and then I have to also change this to be liters instead of milliliters, and then we can do that. So in order to find the number of moles of this from the number of grams, I'm going to have to find the molecular weight, and I do that by adding up the weights on the periodic table. I have one hydrogen, and each hydrogen is 1.01. I have one nitrogen, and each nitrogen is 14.0. And I have 3 oxygens, and each oxygen is 16.0. But I have 3 of them, so that's going to be 48.0. When I add all of these up, let me write this over here. When I add these up, I get 53.01. But again, because this is my last column of sig figs, when I'm adding, I am going to make it just be 53.0. So I have 53, sorry, I made a mistake. I should have carried the 1, and this would be a 63. 63.0 grams per mole. We can always, whenever we're adding up AMUs, we can always say that this is going to be 63.0 grams per mole. So I know if I have 124.3 grams, 124.3 grams times 63.0 grams per mole, I'm going to end up with 1.97 moles of HNO3. So now I have the number of moles per liter. I need to use the number of liters and not the number of milliliters, but that's pretty easy. That's going to be 0.250 liters, and it's actually 0.2500 if I'm going to be keeping track of significant figures. So I have 1.97 moles divided by 250. Oops, I did that backwards. I've got to make sure I use my liters and not milliliters. So by 0.2500 liters, and I end up getting 7.88 molar HNO3. Does that help? I know we did some of these in lab today, but I just wanted to make sure you had some more examples on how to do that. Okay. And now to talk about dilution. Say we already have a solution, a beaker of, let's say we'll call this 12 molar HCl. And we want to make, and let's say there's 50 milliliters, we'll say 50 milliliters. We have 50 milliliters of 12 molar HCl. And for some reason, we don't want 12 molar HCl. We want 3 molar HCl. And when we need 50 moles, we need to figure out how much of this we need to put in here and then dilute to another volume in order to get the volume that we actually care about, the volume that we actually want. And so to do that, we are going to use the dilution equation. The dilution equation says the molarity of the first one times the volume of the first one is going to equal the molarity of the second one times the volume of the second one. Okay, so how do we do that? We have 50 milliliters, but we don't need to use all 50 milliliters. That's just the total that we have. And if we want to make 50 milliliters here, our volume here is going to be 50 milliliters, and our concentration, our molarity, is going to be 3 molar. How much of this are we going to need to put in here and then dilute it up to 50 milliliters in order to get the concentration that we want? So what we'll do is say we need 50 milliliters of this whole solution at a concentration of this. So 3.0 is the molarity times 50 mils is going to be, the concentration of this one is 12, and the volume that we're going to take from here, we know we have a limit of 50 milliliters, so we're going to just call that X. We don't know how much we're going to take from here. We just know that we have a total volume right now of 50 milliliters. So to figure out how much of this I need to take out of here and put into here, I'm going to solve for X. So X is going to be, this times this is 15 over 12, which is 1 3/12, or 1 1/4, or 1.25 milliliters of this solution should be taken out and put into here, and then this should be diluted with enough water to make this 50 milliliters, and that will be a 3 molar solution rather than the 12 molar solution that we started with. Does that make sense? Why does this work? This is an interesting little thing, this dilution equation, right? Well, how does this work? Well, if we think about it, the amount that we take out of here is going to be the volume, and it's 12 molar concentration. We can't really change the concentration that it already is, right? So that we can't really change that, but we can say that if I have 12 moles per liter, and I want to take 1.25 milliliters, 1.25 milliliters, then I can do the math. 1,000 milliliters, and this milliliters will cross off, and my answer will actually be something that is just the total number of moles of HCl that I actually started with when I took out that 1.25 milliliter. So I would have a total mass, or a total, not concentration, but I have a concentration of it. But when I take out a particular volume, I'm taking out a particular number of moles. And that's the only moles of that solution that I'm going to end up over here. So I'm going to have the same number of moles. And if I multiply that by the total volume that I'm going to want over here, you can work it out so that this is actually going to give me the same number of moles that I would have over here, which is kind of a confusing way to think about it. But we'll keep going. Let's look at example 10.5. It says a chemist wants to dilute 12.0 molar HCl to make 500 mils of a 3.5 molar HCl solution. How will he do this? So again, we've got a beaker over here, and this beaker has 12.0 molar HCl, and it doesn't say how much we have, that's the concentration. It doesn't say how much we need. But we need another beaker, and this beaker is going to have, we need to have 500.0 milliliters of a 3.5 molar solution. Okay, oh, you can't see that. How's that? So this is what we need. And we have another container. We don't know how much is in that container, but we do know that it has 12 molar HCl. Again, we can use our dilution equation, which is mV1 equals M2V2. We don't know the volume again that we need, but we do know the molarity. So it's 12.0 times V equals M2, what's the molarity that we are going to want in the end? 3.5. And the volume that we're going to need is 500 milliliters. Now, one question that might be coming up to you is, well, if molarity is always in moles per liter, how is it that I can use milliliters here? And the thing is, as long as you're using the same unit of volume on both sides, it's not going to matter because they're going to cancel off. So you can use a volume of milliliters here, but just remember that this volume is also going to be in milliliters. Okay, so 12.0 V1 equals 3.5 times 500. V1 is going to end up being 3.5 times 500 divided by 12.0. And you can multiply this out on your calculator. 3.5 times 500 divided by 12, and you're going to end up getting 150 milliliters, or 1.5 times 10 squared milliliters. It's worth doing a quick check to see how many sig figs we needed. Here we had 3 sig figs, 1, 2, 3. Here we had 2, 1, 2. And here we had, well, probably just 1, unless it was, oh, look up here, it had 500.0. That's 4 sig figs. So we had 4, 3, and 3, or 4, 2, and 3 sig figs. Our final answer should just have 2 sig figs, which is why this is the preferred way of writing it. This also works, 150 milliliters. But there is some ambiguity. Some people will forget to count, will try to count that 0 as a significant figure, when in fact it is not. It should be written as 1.5 times 10 squared milliliters, and that's how many milliliters you want. So I hope that helps you with the dilution equation. Okay. There's another dilution equation on the next page, 338. A chemist takes 2.5 liters of a 5.6 molar sodium hydroxide and dilutes it with enough water to make 10.0 liters. What is the new concentration? Okay, so over here we have a beaker with 5.6 molar NaOH, and there are 2.5 liters of that. And he takes the whole thing and he dumps it into a larger beaker, and then he dilutes all of it up to 10 liters. So what is the concentration? We don't know, but we can use our trusty dilution equation to figure it out. So our dilution equation says that we're going to take the 5.6 molar times 2.5 liters, and that's going to equal that molarity times 10.0 liters. And again, I've got 2 sig figs here, 2 sig figs there, 3 sig figs there. My final answer is going to have just 2 sig figs. So when I get M by itself, it's 5.6 times 2.5 divided by 10.0. Plug that into my calculator, and the answer is going to be 1.4 molar. And that's going to be the concentration of this. So we went from a 5.6 molarity down to a 1.4 molarity just by adding water to our stuff. Now, sometimes people like to see this done with units, so let me try that again so you can see what's going on with our units. 5.6 molar times 2.5 liters divided by 10 liters. This liter and this liter crosses off, so our final answer is going to be molar solution. And again, this is molar NaOH. So you can see how those units just kind of cross off, and I've got one on the top and one on the bottom. Okay, so again, dilution equation, know that one, put it on your reference sheet. It's a good one to keep in mind. You can use it for all kinds of different things. So keep on going throughout the book. We're going to do a little bit of stoichiometry, which is our favorite thing to do. Concentration shows up in stoichiometry all the time. It's a really, really important concept. I promise that when you take your college chemistry class that this will show up. And because you know it and all of your classmates don't, you will be way ahead in getting the work done quickly and efficiently without a lot of trouble. I know from when I was teaching college chemistry that the students who had seen this in high school were way ahead of the students who hadn't seen this in high school. This is one of the reasons you're supposed to take chemistry in high school and make college that much easier. Honest, it does. So let us look at this balanced chemical equation. 2HCl plus BaOH2 yields BaCl2 plus 2H2O. Okay. That's a nice little chemical equation, isn't it? Okay. Is it balanced? I'm seeing, let's see, 2 H's, 4 H's on this side. Oh, but there's those 2 here. So there's 4 H's, 2 oxygens, barium, 1 barium, 2 chlorides, and 2 chlorides. Yep, we're balanced. Everything looks good. Now let's say I have 100 milliliters of muriatic acid and a lot more barium hydroxide. So we should be able to calculate the limiting reactant from this. So if I have 100.0 milliliters here of this one, and I have excess this, so I've got more than enough of this to react with all of that, I should be able to figure out how much of these 2 reactants I get, because all of this will be used up. It says that I have excess barium hydroxide. So let's figure out how much barium chloride will be produced. And the way I'm going to do this is stoichiometry. Now remember, I already started with a balanced chemical equation. If the equation is not balanced, you will not do this problem correctly. You've got to have it balanced first. I know you know how to do that, so that isn't much trouble at all. So I have 100 milliliters of this, and if I know that this is muriatic acid, it's not just 100 milliliters of this, it's actually 100 milliliters of muriatic acid. And muriatic acid is 9.5 molar. So that means 9.5 moles per every liter. How am I going to figure out how many moles of HCl I actually have if there's 9.5 moles for every 1 liter? If you said I can multiply by the volume here, you're right. So let me write this another way just to make it a little bit easier. I have 9.5 moles for every 1,000 milliliters. Is that the same thing? It should be, since 1,000 milliliters is 1 liter. And now I'm going to multiply this by 100 milliliters of the muriatic acid that I have. And I'm going to find that I have 0.95 moles of HCl. Okay, does that make sense? 9.5 times 100 divided by 1,000 should give you 0.95. If you have any questions on that, I would be happy to answer them. Just bring them into class. No worries about that. So now that we have the number of moles of HCl, we still want to figure out how many grams of barium chloride I'm going to end up with. Just double check that. The grams of barium chloride, it just says how much would be produced. So if I have 0.95 moles of HCl, 0.95 moles of HCl, and I know that for every 2 moles of HCl, I make 1 mole of barium chloride, right? That's what my balanced chemical equation tells me. It tells me I need 2 moles of this for every 1 mole of that. So 2 moles of HCl makes 1 mole of barium chloride. And I'm going to find out from this that I will actually make 0.48 moles of barium chloride. Now, most of us don't have a real good handle on how much 0.48 moles of barium chloride is. So why don't we change moles of barium chloride to grams of barium chloride so we had an idea of how much this stuff is going to weigh at least. So how do I change from moles to grams? I hope you said that I need the molecular weight from the periodic table. So barium weighs, let me look this up. Barium weighs on my periodic table. Let's see if you can see it too. Barium is right here, and it weighs 137.3. 137.3. And chloride on the same periodic table weighs 35.5. So chloride is 35.5, but I've got 2 of them, so that's going to be 71. 71. And when I add those together, 7 and 1 is 8, 10. Yeah, mass of that molecule is going to be 208.3. So 0.48 moles of barium chloride is what I have. And I know that 208.3 grams of barium chloride for every 1 mole of barium chloride. And when I multiply these out, I'm going to get 1.0 times 10 squared grams of barium chloride. Now think for 1 minute before you move on. Why did I write? Because if I multiply this out, it's going to look like 100, right? Because 1.0 times 10 squared is 100. So why did I not just write 100 grams? Well, I know from my starting materials that I should end up with 2 sig figs, right? I have 9.5 molar and I have 100.0 milliliters. So there's 4 sig figs here, there's 2 sig figs here. So 2 sig figs all the way through to the end. And this, it's really hard to tell if that's 2 sig figs or if it's 3 sig figs or if it's 1 sig fig. Technically speaking, this would be 1 significant figure. So I need to come up here and write this in scientific notation so it's explicitly clear that it's 1.0 times 10 to the second grams of barium chloride with 2 sig figs. That's the only way I can see that work. Okay. I hope that's making some sense. And I think the rest of it you should be able to get on your own without a lot of consternation. Really excited about doing the acid-base titration next week. I think that's going to be a lot of fun. So make sure you study up on that. And we will continue doing more of this next week in class. See you on Tuesday. Enjoy your homework.